Hi everyone. In this lecture, we are going to discuss about the middle ear transformer action. The sound travels in the ear as change in sound pressures, but the true organ of hearing remains in the inner ear amidst the inner ear fluids. Sound travels in the ear, which is a less denser medium. Hence, the air medium gives lesser impedance to the flow of sound energy, whereas fluid medium is comparatively denser than the air medium. Hence, it gives more impedance to the flow of sound energy. The sound when travels from air to fluid medium, it is noted that only 0.1% of the sound enters into the cochlear fluids. Rest of the sound gets reflected back. This corresponds to a drop of 40 dB when the sound from the air enters into the inner ear fluids. This change in impedance from the air to the fluid mechanism is called as impedance mismatch. The middle ear helps to overcome this impedance mismatch through a mechanical transformer action. This mechanical transformer action of the middle ear is brought about by the area ratio of the membranes in the middle ear, the curved membrane or buckling effect of tympanic membrane, the lever action of ossicles. Moving on to the area ratio, the pressure is defined as force exerted per unit area. As we know, the area of the tympanic membrane is always larger than the area of the oval window. Now, by this formula, if we see for the same amount of sound pressure level, the force exerted on a larger area of the tympanic membrane will be less compared to the area of oval window, which is reduced. Smaller area of oval window will receive more amount of force. The area of tympanic membrane is 64.3 millimeters square, where Bekesi stated that it is around 85 millimeters square. But the area of oval window is just 3.2 millimeters square. The effective vibratory area of tympanic membrane is around 55 millimeters square. That is, this area corresponds to the pars tensa region. This pars tensa region and the manubrium of malleus vibrates as a single unit till the frequency is 2 kHz. When the frequencies go beyond 2 kHz, there is a small lag between the vibration of the tympanic membrane and the handle of malleus. Now, the effective vibratory area or the area ratio of the membranes in the middle ear corresponds to 55 divided by 3.2. So that gives a ratio of 17.2. That means the force experienced or felt at the level of tympanic membrane is multiplied by 17.2 times when it reaches the oval window, provided the ossicles act as a single unit between the tympanic membrane and the oval window. The curved membrane mechanism was first explained by Helmholtz in 1868. He stated that the tympanic membrane is held tightly along its rim in the tympanic annulus. The center of the tympanic membrane is connected to the handle of malleus through manubrium. Now, these free surfaces are free to vibrate, whereas the movement is restricted at the level of manubrium. This enables the tympanic membrane to function as a lever action. He explained this as lever action of tympanic membrane. According to the formula for lever action, the product of force and displacement on one side of the lever should be equal to the product of force and displacement on the other side. Now, when these regions are free to move, there will be greater displacements. Hence, lesser amount of force is required to vibrate this region. Whereas the movement is restricted at the region of manubrium, hence more amount of force can be felt over there. This contribution of tympanic membrane for the middle ear transformer action was re-evaluated by Tondorf and Khanna in 1970, where they coined the term as buckling effect. They found out that the manubrium attachment has made two regions of vibrations for any sounds below 1500 Hz. They found out that tympanic membrane does not vibrate as a single unit, rather than it vibrates as two different units due to the attachment of manubrium. Now, above 1500 Hz, this vibratory pattern, rather than two different parts, a complex pattern is seen at the tympanic membrane. Hence, they reported that the transformer function of the middle ear is increased by 2 times because of this buckling membrane effect. The ossicles function as a lever in the middle ear. The ossicles rotates along the axis of rotation formed by the posterior incudal ligament and anterior malleolar ligament. The malleoincudal joint acts as the fulcrum for the lever. The handle of malleus forms one of the arm of the lever and the long process of incus forms the other arm. Now the length of the malleus and incus is differing. To understand that, let us see this lever where the longer length of the malleus and shorter length of the incus. So greater distance moved over here requires lesser amount of force, but the same energy when it is going to the other side, as the displacement is reduced, greater force will be felt. The length of malleus is around 9 mm, whereas the length of incus is 7 mm. This brings about a ratio of 1.3, which means the force given at the handle of malleus is increased by 1.3 times at the long process of incus. Now, the total contribution of middle ear transformer action is brought about by the area ratio of the membranes in the middle ear, which increases the force by 17.2 times, and the buckling membrane effect of the tympanic membrane, which increases the factor by 2, followed by the lever mechanism of the ossicles, which is going to enhance the transformer function by a factor of 1.3. The product of these three mechanisms is equal to 44.7, which means the force experienced or felt at the level of tympanic membrane is going to be multiplied by 44.7 times when it reaches the inner ear. When it is converted into decibel scale, it corresponds to 33 decibels, which means the middle ear transformer action is going to enhance the sound by 33 dB. The same when calculated at cats. The cat's middle ear transformer action corresponded to 36.8 dB through these calculations. However, when the transformer action was analyzed for cats, we didn't get that much amount of boost from the middle ear transformer action. These are based on various assumptions. The ossicles do not act as a single unit. Also, there are soft tissues in the middle ear cavity which can absorb sounds. And the transformer action is not constant across all frequencies. It varies. Moeller in 1960 stated that the human middle ear system has a major resonant peak around 1200 Hz and a minor resonant peak around 800 Hz. The normal middle ear reactance values based on 20 studies were summarized by Margolis, Van Camp, Wilson and Critton in 1985. They found out that the reactance was 0 between the frequencies 800 Hz to 5000 Hz. The reactance is equal to 0 means the stiffness component and mass component of the middle ear are same, which means the middle ear is at its resonance, allowing the sound energy to easily pass through them. The frequencies that travel with maximum efficiency through the middle ear are 800 Hz to 5000 Hz. There is greater attenuation below 800 Hz and some of attenuation above 5000 Hz. So the middle ear is more efficient in transferring frequencies between 800 Hz to 5000 Hz. That is called the resonant frequency of the middle ear. This is the reference used for this particular lecture. Hope we have understood the middle ear transformer action in a simpler terms. Thank you.